The trick for finding the center of mass for an object like this broom, if you start with your fingers far apart and you bring them together quickly, you will automatically bring them together at the balance point. The balance point is another name for the center of mass. It's not the point where you have equal mass on either side, it's the point where you have equal torques on either side. So actually this side is heavier because it's much closer to the fulcrum, but the center of mass is the average position by mass. And it's an important point because if you look at this point right here, if I were to throw this broom across the room, that point is going to move in a nice parabola, even though the broom might be flipping end over end, because it's as if I had taken all the mass and condensed it down to a single point. That point will move translationally. That center of mass point will move translationally just like that. So how do you find the center of mass for an object that's kind of odd shaped, like this wrench here? There's a trick for doing it. All you need to do is hang it by two different points. And if you have a vertical line hanging down, where those vertical lines cross is going to be the center of mass. So I'm going to trace out that vertical line when I have it hanging from the top, and then conveniently I have a hole in the bottom of the crescent wrench that I can hang it from. It doesn't matter which 2 points you hang it from, as long as you draw vertical lines when it's hanging in those positions where those vertical lines cross is going to be the center of mass. So we'll see if we can get the chalk side out. All right, looks like they're crossing. So you can see right about there is the center of mass. All right, I got my special bird out that has the center of mass right on his beak. He's got weighted wings so that he can balance on that perch. And I thought that would be a really neat trick if I could use the center of mass that I found for my crescent wrench, which is kind of hard to balance, and somehow get it to balance on this bird's perch. So we'll try this out. I know it's close. There we go. So why are we talking about the center of mass in this unit on momentum? Well, turns out that if the center of mass for a system is at rest, then the center of mass will stay at rest. And if the center of mass is following some trajectory, and all of a sudden there's maybe an explosion midair or something, the center of mass of all those pieces that exploded are still going to land at the same point that they would have landed at even if there wasn't an explosion. So for any kind of closed system, the center of mass is going to follow the laws of motion. So that's why when we look at collisions, we sometimes will analyze the center of mass as motion. All right, if you're going to put together a mobile, like maybe for over someone's crib or something, you should probably know something about the center of mass. So if you look, each level is hanging from the center of mass. So this really shows that the center of mass is not the point where the mass is the same on both sides. You can see that I have all the stuff on the right and only one single board on the left. But that single board is far from the pivot point. So the center of mass is the average position by mass. And so the average position is way over there on the right when you consider all the stuff. So how do you find the average position by mass for some particles? Well, this isn't exactly a system of particles because the meter stick weighs something. It's close though. So we have three different weights. I've got a 200, no, actually that's a 100 at the 4 centimeter point, which is 46 centimeters from the fulcrum. And then I have a 200 at about 60 centimeters. And then I have a 50 down there at about 96 centimeters or so. So the reason that this is balanced is because the torques are equal on both sides, meaning that the force times the distance to the fulcrum for the one object on the left is equal to the force times the distance to the fulcrum for this object plus the force times the distance to the fulcrum for that object. It's actually also true that the masses times the distance on the right is equal to the mass times the distance on the left, because they're all being acted on by the same 9.8 meter per second squared acceleration of gravity. So this kind of gives you a way to find the average position of mass. And in this case, the average position of mass is the fulcrum for those three masses, or really close. But what you can do is you can take each object's position times its mass and then divide that by the total mass of the system, and it will give you that average position of mass. It looks like the 100 grams on the left is being balanced by nothing, but the meter stick has mass, and the meter stick's mass actually all acts at its center of mass, like you had a weight here at the 50 centimeter point, which was equal to the weight of the full meter stick. And that's able to balance out that 100 grams, so about 19 centimeters from the fulcrum, because the meter stick's mass is 31 centimeters from the fulcrum.